So in this first problem that we are going to solve, you can see the statement of the problem over here. You can pause the screen to get rid of it. What we have is a cone with two particles, P1 and P2, which are connected by a string of constant length L. This string goes through the vertex of the cone and connects the two particles. P1 must move on the surface of the cone, so it can basically slide up and down and around the cone, while P2 can only move up and down the axis of the cone. Both P1 on the surface of the cone and the string on the vertex can slide without any friction. Okay? So, as with every problem in mechanics, we are going to start with the kinematics of the problem. We are going to first write down the position, velocity and acceleration of the two particles in a set of coordinates, right, using vectors of different reference frames. And then we are going to move on to the dynamics, and we are going to state the equations of motion. That's basically the three first questions in the problem over here, okay? And then, as with many problems, there are several other questions that may relate to what has been done before and are basically specific questions of that problem, as we will see later. So, let's move on to the kinematics of the problem. Alright, so as always with kinematics, one of the first things that we have to do is to define the vector basis that we are going to use throughout the problem. We are given one reference frame, XYZ, as you can see over here, and this is an inertial reference frame in which we have to provide our answer, alright, but we can define several auxiliary reference frames and bases that can help us solve the problem. So one of the first reference frames that I'm going to introduce is the rotated reference frame, as you can see over here, alright. Okay, that would be x1, y1, and c1, okay, which is rotated at an angle theta with respect to xyz. This reference frame has the following vectors, which we should write down before using them. So the unit vectors for this reference frame, ijk, with subindex 1. In the case of I1, that is basically the rotation of this vector over here. That gives me cosine of theta I0, okay, plus sine theta J0. Then we have I1, which is the rotation of I in this direction. So the vector J associated to this y-axis gives me minus sine theta I0 plus cosine theta J0. And then finally we have the vertical vector, which stays the same under the rotation, and therefore K1 is equal to K0. Okay? So that's one of the reference frames that we are going to use, and actually we can solve the whole problem with just that one. It may be interesting, however, to introduce a second one, alright? I'm not going to use it in this solution, but it's also possible to do it, which would be a second rotation about the y1 axis, okay? A rotation in this direction, which brings the x1 axis into this direction, okay? We can call this direction x2, and the vertical direction then becomes something like this. That would be c2. And y2 is the same as y1, alright? That reference frame, in case we wanted to use it, would be written like this. So since it is a rotation about y1, okay, j2 is equal to j1. That's the easy part, okay? The angle that we have rotated this is the complementary angle to the half angle of the cone, which we will call alpha, okay? So this is the angle 90 degrees minus alpha, okay? Pi half minus alpha. That means that the vector, sorry, from here to here, the vector that, the rotation that goes from here to here gives me I2 vector, which is equal to sine alpha I1 plus minus cosine alpha K1, okay? And in the case of K2, the vector is cosine alpha I1 plus sine alpha K1. Okay, that is the vector over here. So next step, once we have defined these vectors, all right, is to decide how many degrees of freedom the problem has. And as you can see, we have two particles, P1 and P2. If these particles were moving in free space, in 3D space, they would have each of them 3 degrees of freedom, okay? However, P1 has to move on the surface of a cone, okay? And P2 can only move up and down this line, all right? These constraints reduce the number of effective degrees of freedom, in this case from 3 to 2, okay? P1 can move in 2 directions, and in the case of P2, to only 1, okay? They can only move up and down. Apart from the constraints of the cone and the vertical line, we also have the constraint of the string, which further removes 1 effective degree of freedom. In essence, the whole system, the two particles together, has only 2 degrees of freedom, 2 effective degrees of freedom. So in principle, we only require 2 coordinates to describe the whole configuration of the system, okay? And in this case, in this problem, we are already suggested which are the coordinates that we should use. We have theta, okay, which basically tells us what is the position of this segment of the line around the cone, all right? And then we have he, which is this letter over here, which tells us which part of the string is on the surface of the cone, like this. All right, so we are going to choose he and theta as the coordinates to solve this problem. As with many other problems, there are constants in it. Okay, there are some parameters that are not time dependent. In this case, we have 3 constants. Okay, we have the mass of the particles, which is equal to m for both of them. We have the acceleration due to gravity, g, and we have the length of the string. Apart from that, we also have the half angle of the cone, alpha. So we have a total of 4 constants in this problem. Okay, just remember that when you take derivatives in the expressions, these are constants, so you don't need to take derivatives of them. You just have to consider them as constants. Okay, the next step is to write down the position vector of P1 and P2 and take derivatives there to obtain the velocity and acceleration of each of the particles in the inertial reference frame. Okay, that's what we basically call the kinematics of the problem. So let us start with P1. We are going to write down the position vector of P1. Okay, let's use superindex 1 to denote particle P1. And since we are working in the reference frame 0, okay, the inertial one given to us, that will be the position with respect to that reference frame. We write down this position using, I'm going to use the red reference frame here, okay, so I'm only going to use this vector basis, all right. As I said, I could be using this other one, all right, but in my experience, this one is enough to solve the problem, so let's just stay with this one. So the position of P1 is essentially on the surface of this cone, okay, and it is a distance he from the origin, all right, and in the direction of I2, okay, which I have over here. This vector is partly in the direction of I1, okay. This distance projected along x1 gives me the sine of alpha, right? And part of it is in the minus k direction, right? And that is this much, cosine of alpha k1. Okay. So now that we have that, we can take derivatives over here to obtain the velocity and the acceleration. And in doing that, since we are going to take derivatives in time in the inertial reference frame 0, okay, we have to keep in mind that vectors I1 and J1 later are not constant. So they will produce some derivatives that we have to consider. So the velocity comes out of taking derivatives over here. First, applying the chain rule, we have the derivative of he, okay, and then we have he sine alpha times the derivative of I1, okay. I1, as you can see over here, we can basically take derivatives on the definition over here. If I did that, I could find that the derivative of I1 in time in reference frame 0 is equal to theta dot J1. Okay, that's very easy to prove. So we write that over here and we obtain this second term after applying the chain rule to the first term in the position. The second one over here just gives me one term, which is due to the derivative of he. Remember that alpha is a constant in this problem. So we just get this, okay? And then moving on to the acceleration, which requires an additional step of derivation, we have the second derivative of he, sine alpha, I1, plus he theta dot sine alpha J1 after taking derivatives over here like before, okay? Then we move to the second term. This gives me another term just like this one when I take derivatives of he, so I can just put the 2 over here, alright, plus a term that has the second derivative of he of theta, sine alpha J1, and then the derivative of J1, okay, just as we did before, the derivative of J1 in time in reference frame 0, that gives me, in this case, it's minus theta dot I1, okay. So that term produces this additional term over here, he theta dot square sine alpha I1, okay. And finally we have the last term remaining, so that gives me the second derivative of he cosine alpha K1, alright. So that basically is the kinematics of particle 1. Let's move on to the kinematics of particle 2, which are far more simple because, well, the particle 2 can only move up and down the line. So its position vector, the particle 2 in reference frame 0, is something that we can write. Remember that the length of the string is L, okay? And since we have this part of the string which is he, the rest of it, which hangs along the axis of the cone, is L minus he, okay? And since this is hanging below the xy plane, it's a negative c direction, we write it as minus L minus he K0. Okay, we can use K0 or K1, it's no matter here. Since we are using 1 above, let's just use it. Remember that they are the same, the two vectors. So now we take derivatives again to obtain the velocity, okay? In this case, L is a constant, so the only thing that gives me a derivative is he. We just get this. And the acceleration is just the second derivative of he in the vertical direction, okay? So that concludes the kinematics of the problem. We have solved for the position, velocity and acceleration of the two particles, and these expressions are essential for what comes next. Okay, so the first thing in the dynamics of the study of the dynamics of the particles is to write down, identify and write down all the forces that are acting on them. So if we consider P1, for example, we can see that since this is a heavy particle with mass m and there is a gravity vector over here, there is a weight force pointing downwards, okay, which we are going to write as W1, okay, and its mathematical expression is minus mg in the K1 direction. All right. Now, on P1, there are two additional forces acting on it. The first one, since we are on the surface of a cone, okay, and the particle cannot move perpendicular to it, there must be a reaction force perpendicular to the surface of the cone, which we are going to call N. Okay, this normal reaction force is a reaction force, and therefore we don't know its magnitude, okay, but we can at least provide its direction. The direction of N is the perpendicular to the cone, as I said before, so we actually have a vector in that direction. Is the same vector as I2, okay, which we have from our study of the kinematics, is this direction, alright? If you haven't computed this basis, this is not a problem. You can work it out, you can work out this direction from the sine and cosine of the angle alpha over here, okay? So this gives me an unknown magnitude of the force, which we are going to call N, and then the direction of this vector goes like this. So this is in the direction cosine alpha I1 plus sine alpha J1. I'm sorry, this is K1. Okay. And finally, there is a third force acting on P1, which is the tension of the string itself. Okay. This is again a reaction force. We don't know a priori how much this force is. So we are going to introduce this with an unknown T, okay? And the direction is the same as the position vector of P1, except that in reverse, all right? So this gives me sine alpha I1, okay? And then minus cosine alpha K1. Now these are the three forces that are acting on P1. Let's move on. Let's move on to particle 2. So for P2, there are essentially two forces. There is the weight, just like before. Okay, so there is the weight of particle 2, which again has the same expression. Okay, and there is also the tension. All right. Now, something important here that we must realize is that the tension of the force, the tension of the string, sorry, since it's basically a continuum and there is no friction on the cone over here, the tension, the magnitude of the tension is constant along the string, all right? So we don't need to introduce an additional unknown, a different value of T for the tension here and the tension here, all right? The tension is going to be the same. So if we call the tension before T1 and the tension for particle 2 T2, the magnitude is going to be the same. It's going to be equal to T. And its direction in this case is along the vertical positive, okay? So these are all the forces in the problem, in the two particles, okay? And we are going to use these expressions to write down the equations of motion. We need to use the vector equation from the second law of Newton, okay, for particle 1. This is going to be equal to the sum of all the forces on P1, okay? And we are going to use also the equation of Newton on particle 2, on P2. Okay? The combined expressions that we get from here are going to provide with a set of differential equations that we can solve to obtain the solution of the motion of the two particles. So starting with particle 1, okay, we have our acceleration from the kinematics, all right? And we have our forces over here. We only need to choose in which three directions to project this vector equation, okay? So since I have already written down the acceleration and the forces using the basis B1, okay, I1, J1, and K1, I'm going to use these same three directions to project the vector equation over here to obtain the three scalar equations. So if I project along I1, okay, the equation that I get is everything that goes in the direction of I1 over here times the mass of P1, okay, so that gives me second derivative, sine of alpha, and then this additional term over here, theta dot square sine alpha, okay, and there are no others. This has to be equal to all the force components for P1 in the direction of I1. And as I can see, there is one here and one here. So this goes into this, cosine alpha plus T sine alpha. I realize now that there should be a minus on this tension force, okay, because it's pointing in the direction of minus the direction of the vector that goes from O to P1, the position vector of P1. Okay, so there should be a minus there if we want to keep T positive when there is tension on the string. All right. So sorry about that. That means that here T appears with a minus. Okay. Let's move on to the projection along J1. Okay, so here we have these two terms of the acceleration of P1 that we must consider. So there is this one times the sine of alpha plus this one sine alpha, and then all the terms that go in the direction of J1 in the forces. And as you can see, there is none. All right, that's an interesting result. We just have to write a 0 over here. And finally, for the vertical direction, we have just this term, okay? So this is he second cosine alpha, and all the forces that have a component along K1. That gives me minus mg for the weight, then plus n sine alpha for the normal reaction force, and then plus T cosine alpha for the tension. For particle 2, as you can see, we could write the three equations of motion of P2, but there is only one interesting direction to consider, which is the vertical one. All right? If we wanted to consider the directions outside of this line, we should include two additional reaction forces, which force the particle to stay on this line. All right? But we would get trivial equations. Since the acceleration outside of this line is 0, we will just get immediately that these additional reaction forces are equal to 0. So we are going to skip that, and we are just going to obtain the equation along the vertical direction K1 for particle 2. All right, this gives us m times the second derivative of he, and this must equal all the forces in the vertical direction, which is minus mg plus t. Okay, so these are the four equations of motion that, if integrated, would give us the evolution in time of he and theta, okay, the two coordinates that we are using to describe the configuration of the system, and additionally that will give us the value of n and t along time. All right. Usually what we do with such a system of equations is to work out a linear combination of equations that does not contain the reaction forces. All right. So for example, if we wanted, we could solve for t in this equation and use that equation to eliminate t in these two equations over here. All right. And then if we multiply this equation by sine and this equation by cosine of alpha, and we subtract the two equations, all right, the terms involving n would also disappear. Okay, so that is also useful to eliminate n. And only then, when we have two equations, one for he and another for theta that do not depend on the reactions, we can integrate the problem, and only afterwards, when we have this, the value of these two coordinates in time, we can go back to the two remaining equations, all right, and obtain the value of t and n by substitution. That's the usual approach that we follow in mechanics. Okay, so once we have the kinematics and the dynamics of the problem, we are ready to take on the next questions of the problem. The specific questions which are very particular to this problem over here. If we look, for example, at question number 4, all right, they ask us what is the condition that he should satisfy in order to ensure that the tension on the string remains positive at all times. All right. In other words, we want to avoid that the string becomes slack. Now, this is something that can be very easily understood if we look at the equations of motion that we have from the last step. Okay. In particular, if you look at the fourth equation, all right, this is an equation that is extremely useful for this question, since we can solve for t as a function of he and constants of the problem. All right. So if we just solve for t in this equation, we see that t is equal to m he second plus g. All right. So all we want is that this be greater than 0. That's what the question is asking us to do, right? So clearly the condition that he must satisfy, actually its second derivative must satisfy, is that it has to be larger than minus g. As long as this is true, the tension on the string is always going to remain larger than 0. So moving on to question number 5, what we are asked here is what is the condition that theta should satisfy, actually what is the velocity of theta, the rate of change of theta, in order to make P1 describe a parallel of the cylinder. Okay, so we want to know what are the conditions that avoid P1 to move up and down the cone and just slide in the theta direction. Okay, so again we go into our equations of motion, all right, which we see here, and we notice that if theta describes, this particle describes this type of motion, he remains constant. Okay, that's an important thing to keep in mind. He equals constant. That means that he dot and he second are equal to 0. All right. So we can enter with this condition into the equations of motion and particularize them to answer this question. So we just copy over the 4 equations that we have here, but we will replace he dot and he second by 0. Okay, so for the first one, we just get m minus he theta dot square sine alpha, okay, equals n cosine alpha minus t sine alpha. For the second one, we get m he theta second sine alpha equals 0. For the third one, we just get all the left hand side is equal to 0. So minus mg plus n sine alpha plus t cosine alpha. And from the fourth equation over here, what we learn is that t has to be equal to mg when this is 0. Okay, so that's also an interesting result that we can use. All right, so we have these 4 equations and we have to reach the conclusion of what is the value of the angular velocity theta dot in order to have this type of motion. The particle P1 describes parallels of the cone. So from this equation over here, the second equation, we immediately see that theta second is equal to 0. Therefore, theta dot has to be constant. That's the only way where we can achieve this type of motion. All right? Let us use the remaining 3 equations. First, we are going to use this last equation to remove t in these 2 by replacing it with mg. Okay? And then I'm going to multiply this first equation by sine alpha, this second equation by cosine alpha, and I'm going to subtract the 2 equations together. The result will remove n. Okay, so let's just do that. I'm going to start writing the first equation multiplied by sine and with t replaced with mg. The equation that results is this one. Sine square alpha n cosine alpha sine alpha minus mg sine alpha square. Okay. For the third one, we get 0. We want to multiply this by the cosine, so mg cosine alpha plus n cosine alpha sine alpha plus t cosine square of alpha. Okay. If we subtract this equation to this one, the result is this. M he theta dot square sine square alpha. This term vanishes with this one, they cancel out, okay? And all that remains is mg cosine alpha with a positive sign from here minus this term over here. Okay. Oh, remember that this was mg. Okay, so this comes here with a minus. Alright, and that's it. That's all the terms that we have. Clearly, we can replace this minus sine square minus cosine square by minus 1. Alright, and then solving for theta dot, what we have is g cosine alpha minus 1 divided by m he sine square of alpha. Okay. Alright, so for the final question, question number 6, what they ask us to do is to find two first integrals of the motion of the particles, alright, which allow us to describe their motion, what is going on with them. Now, this is a question that requires us to think quite a bit, okay? We have to see what type of conserved quantities might be out there. First of all, it's always interesting to see in these type of problems whether the mechanical energy of a particle is conserved or not, alright? Now, I want you to follow me on this. Remember that the condition for the mechanical energy of a particle to be conserved is that all the forces that exert work on the particle, alright, must be conservative. They must derive from a potential. Okay, so if we look at the forces that we have for P1, there was the weight, there was the normal force, and there was the tension, alright? Those were the three forces acting on the particle P1. Now, clearly N1 does not exert any work on P1 because it is always perpendicular to the velocity of P1. P1 must move on the surface of the cone and N is always perpendicular to the cone, alright? Since the force is perpendicular to the velocity, the power associated to that force is always 0 and therefore it does not exert work on the particle, alright? So we don't need to worry about that one, whether it's conservative or not. It's clearly not conservative, okay? In order to check whether the energy equation conservation is applicable or not. For the other two forces, well, the weight does work, okay, because the particle can move up and down along the vertical direction, even if it remains on the surface of the cone. It can move up and down, and therefore there can work on the particle, all right? But so does the tension, all right? The tension is going to work on the particle as it moves up or down, all right? For the weight, it is not a problem because it is a conservative force. We can write down the potential expression from where we can derive this force, okay? But the tension is not conservative. Actually, we don't know the magnitude of the tension until we solve the problem, right? So tension, like any other reaction force, is clearly not conservative. So this tells us that the mechanical energy of particle P1 is not conserved, all right? A similar study of particle P2 tells us there are two forces here, the weight on particle 2, okay, and the tension. We clearly see that, again, the weight is a conservative force, no problem about that, but the tension, which is not, does exert work on the particle, all right? So the energy of P2 is not conserved either, all right? What we can see is something quite interesting. The work that the tension exerts on P1 as it moves in the he direction is equal and opposite to the work that the tension exerts on P2 as it moves down, okay, and vice versa. So as these two particles move up and down and he changes, the tension, which is constant along the string, exerts work on P1 and P2. But the amount of work that it exerts on each of the two particles is is equal and opposite. That means that we can consider the combined mechanical energy of the system, composed by the two particles together. And in that case, the tension becomes an internal force of the problem, okay, is internal to our system, and indeed, the total mechanical energy of P1 plus P2 is a conserved quantity, all right? So that is going to be the first conserved quantity, the first integral of motion that we can write down for question number 6. we have to consider the kinetic energy of the two particles, okay, plus the potential energy of each of the particles together. So let us work first with the kinematics, okay, over here, where we have the expression for the velocity of each of the particles in order to write down the kinetic energy of T1 and the kinetic energy of T2, right? The kinetic energy of T1 is 1/2 times m times the velocity square, alright? So we can just write he dot square sine alpha square plus he theta dot square, each of them, sine of alpha square plus he dot square cosine alpha square. Okay, we can clearly combine these two terms into one. And for particle number 2, we just have 1/2 of m he dot square. Okay? Now, regarding the potential energy of the system, we only have to consider the weight on each of the particles. Okay, so we need to write down the potential associated to the weight of particle 1 and particle 2. Let's start with particle 2. What we want is to multiply mg by the height of the particle along the vertical direction. Okay, the height of the particle is given again by the kinematics. Okay, everything that is multiplying k1. So we can write down mg minus L minus he. That gives me the potential for particle 2. Of course, I can write this down as mg he minus mg L. You can see that this is a constant, okay, and therefore you can actually remove that from the definition of the potential, as the potential is defined except for a constant, an additive constant, that you can add or remove as you please. Okay, so that term over there is not important. The gradient of this gives me the same as the gradient of just this. Alright. Now for the potential of particle 1, I have to consider the vertical position here. So that gives me mg minus he cosine alpha. Okay. Now adding the four terms together gives me, and I'm going to simplify these two terms already with this one, okay, that gives me m he dot square for the three of them plus 1/2 of m he square theta dot square sine square of alpha for this one, and then I'm going to try to group together all the terms that depend on mg. Okay, so that gives me plus mg he minus he cosine alpha, okay, which we can write like that. And then this term, as I said, is a constant, so we can just drop it. Okay, we can say that all this is equal to a constant E. Now, we have obtained this expression for the conservation of the mechanical energy of the system by reasoning in a physical way. We have understood that the forces that exert work and are external to the system, which is only the weight on the two particles, are conservative forces, and therefore the mechanical energy of the whole system has to be conserved, right? But we could have also reached that result by working on the equations of motion, okay? This is a little bit more involved, but it's also possible to do. We can first remove the reaction forces, okay, as I showed before. We can use this one to remove T over here, and we can find a linear combination of these two equations that does not depend on N. And then we have this equation plus that new one, which are basically two equations for our 2 degrees of freedom, theta and he, which do not depend on the reactions, all right? By working with these expressions, we actually need to multiply them by an integrating factor. We can then integrate them and we will reach exactly the same result as we reach over here, all right? Remember that the equation of mechanical energy is not an independent equation, all right? It does not add additional information with respect to the equations of motion, all right? It's actually an integral of a linear combination of them, all right? So It is not adding new information to our problem. The second conserved quantity that we can find is perhaps a little bit more involved, but there is a very interesting clue in the equations of motion. We can see that the second equation has a right-hand side that is equal to 0. All right? That means that if this is an exact derivative of something, that something is conserved in time. All right? So clearly it is difficult to integrate this right away, okay? But as always, we can apply some tricks. So if we look at this equation, we cannot integrate it right away. But if we multiply it by this integrating factor, okay, let me just copy over the equation first. Like this. Okay, I want to multiply it by he sine alpha, okay, for what you will see in a moment. Now, if I solve this product, what I find is, and let me just get rid of m because it's a constant and we can send it dividing to the other side. All right, so we get this. All right, sine square of alpha plus he squared theta second sine square of alpha. Alright, this is equal to 0. Now here perhaps it's now easier to find out what is the integral of this. Okay, maybe you can guess it, but otherwise you can check that he squared theta first, okay, sine square of alpha is the integral of this. Okay, you can check that if you take the derivative of this, you get 2 he dot, and the rest remains the same, plus, applying the chain rule, he square theta second sine square of alpha. Okay, so what this is telling us is that this is a constant. Okay, this is a constant of motion. Now, I'm going to call this constant of motion hz. All right. And I want you to understand what is the meaning of this constant of motion. If we have kept the mass, it would be properly an angular momentum, okay? And indeed, this is the angular momentum of P1 about the vertical axis. Clearly, the forces that we have acting on P1 do not exert any torque with respect to the vertical axis, all right? So the torque that the forces W and T exert with respect to O on P1, okay, there is a torque, but that torque never has any component along the vertical direction. And that means that the vertical component of the angular momentum, hc, is conserved. And finally, to get a feeling of how the system would move in reality, in this video you can see a simulation of the system, okay, which has been executed with MATLAB. You can see the motion of the two particles, all right, and you can see that as particle P1 moves closer to the vertex of the cone, P2 goes down in the vertical axis of the cone and vice versa. In this other plot over here, what you see is the time evolution of the two parameters, theta and he, in the same simulation as before. So you can see that theta basically increases and goes around when it reaches the pi, appears in the minus pi direction, and he oscillates between a minimum and a maximum value. You can find the script used to generate this simulation in the description of this video. And with this we conclude this first problem on mechanics. I hope it was useful for you. Feel free to send us any comments or help on improving our videos in the link that you can see below. Thank you very much.